Hello everyone. So during the lecture I mentioned the numerical and symbolic methods, and that there's a difference in how we approach our problem and what methods we use to manipulate the equations. So first let's start with what's the difference between the numerical and symbolic methods. So symbolic method is what you learn in Calc 1, Calc 2. That's what you're doing all the time. So you have some kind of expression, and this doesn't really have any numerical value. This is just a variable which you can manipulate with the rules of calculus. Like if I assign it to be a function, and now I want to differentiate with respect to x. This is just a symbol. It's abstract. It follows certain rules. So here I know this is d of x squared plus 1 for dx, and for example, this can also be just a symbol. This is c. This is a constant, and there's a rule. If you differentiate constant, it goes to 0. Now, this is another symbol, and it follows the rule of dropping the exponent and x. And this is so symbolic manipulation is just applying the rules of calculus and mathematics to symbol, like integrating our f of x. All those symbols will follow certain rules. So I know I integrate x squared, and the rule is plus 1. And here divide by. So I would get x to the third. And this symbol follows this set of rules. If I were to operate in c, I know I need to multiply it by x. And there's another constant. So those are just the rules. And this is nice. This will give you the exact equation, but it doesn't really give you the values. It just gives you the pattern. Those are just patterns. And with numerical methods, if you actually want to get a number out of your function, like what the value of my function is, if you have a sine function, that's not how your computer sees it. If you want to do anything with it numerically, then how your computer is actually going to process it. It's going to take it, evaluate it at sample points, and this is not stored as a function. It's stored as x, y pairs. And then what it's going to do is going to take your points and it's going to fit a polynomial to it. But those are just numbers. This just became an array of numbers. This is just going to be an array of coefficients of our polynomial. And once we stop operating on symbols, it doesn't follow the rules of calculus anymore, because those are numbers. And first of all, computers have limited precision, so there's certain number of digits, of decimal digits I will fit. So this is not the same. This already lost some information. It might be a minuscule amount, but it is not the same. This is just an array of numbers. And the other thing, you cannot do calculus with numbers, just having the values. So here the definition of the derivative actually starts being what we learn derivative is in Calc 1. So we evaluate the function, take our value from here, evaluate f of x, and so let's take those 2 points. This is our f of x plus h minus f of x over what my change of x was. So we plug in numbers, and once the numbers enter the scene, we lose precision because we cannot store infinite number of digits. There will be rounding and rounding and rounding. And your expression might start with a little error, but the more operations you apply to it, the error might be magnified because on every step there will be an error. So this is the pitfall of numerical computation. There is always an error, but you cannot avoid it. Some things, like Professor Persans mentioned, when you are doing a wave function for more than one electron, you cannot get an expression like the actual function that will relate something to something. You get numbers on some grid, for example, potential in space, and you want to fit a polynomial to it. You want something that is going to fit it. But those are numbers. Those are just numbers, and you cannot apply calculus to it. You have limited precision, and the rules of calculus don't apply anymore. But there's advantage to symbolic manipulation, of course, because if you don't want numbers, if you actually want to know what the derivative of your function is, then you don't want it to be a number, unless you want to evaluate it at the end. But you don't want it to be just a number. You want it to give you cosine of x. So this is symbolic manipulation. And it's done totally differently than numerical values. For numerical computations, you just create arrays of numbers. Number, number, number. For symbolic manipulation, expression starts as a symbol, and then you need to dissect it. Like there's just pattern matching. It stores the exponents and everything, but it stores it as a symbol, not an evaluated. It's not evaluated at any certain point. So this, for example, if I want to deal with it symbolically and I want to differentiate it, so it's here my d is a constant. So I probably should change it to something else. So let's make it c times x squared, and I want to differentiate that. What symbolic manipulation will involve here is just matching the pattern. So take that. Okay, what's my variable? Spot the variable. That's going to be my variable. Okay, so store this as a constant. This is just a constant, but it's a symbol. Multiplying my variable. How do I differentiate? There's a rule. Since this is my exponent, I need to drop it here and subtract 1 from it. And bingo. This is just matching the pattern. And for integrating, that's exactly the same thing, but it's way harder because there's no real set, except for very simple functions, there's no real set of rules. So then you generalize your expression to whatever it is, and you try to match the pattern. There are huge algorithms to check the patterns and then see if this expression, whatever I got from integration, if I apply the rules of differentiation, would it return that? So this is pattern matching. But I also mentioned during the lecture that sometimes when you give our symbolic integrator a function of sine, for example, you don't want it to apply the general algorithm because it's going to take much more time, and you can just tell it, hey, I'm going to do trig integrals. So don't bother looking for polynomials or other patterns. This is a trig. Search for trig that's going to give me that. So this is doing it symbolically. Numerically, this just becomes an array of points, and you apply the finite difference method. So yeah, that's short introduction to numerical and symbolic manipulation, and here comes part 2 when I actually do it in Python. So hello and welcome back, and now we're doing hands-on Python. So first, I'm going to start with importing the libraries I will need. So this is SymPy, Symbolic Python. And from SciPy, I will import the integrate module that will give me the quad function for integration. So here they go, imported. So you need to tell Python that you're going to make a symbol, otherwise we'll just treat it as a normal variable, which we don't want in this case. So here I tell it. Now X is going to stand for a symbol. You're going to apply the rules of calculus, not numerical methods. You're going to apply symbolic manipulation to that X. So this is what this comment does. It assigns the symbolic value to my variable. So I can define another symbol, make it a y. Here it goes. Okay, so I want to perform an integration on my symbol with respect to X. So the syntax is very simple. It's just integrate my expression and what's the variable, because you need to tell it. It's not going to figure it out if you have, like, for example, if I have an A here and let's make it some number, but it's still a number. If I multiply it by A, then it needs to know, hey, you integrate with respect to X. This is just a number. Use it as a number. So, ooh, yeah, run that first. Here we go. Okay, it just substituted. So this is applying the rules of calculus to that. There are no numbers. This is just a symbol. Those are just symbols. Okay, if I want to actually construct an integral out of it, now I'm going to redefine my A, which is super fine with Python, because how variables work in Python is actually this stores an address to an array of addresses that point to the values. So that's why you don't really need to say what type the variable is. It's just an address that starts an address, so it can be reassigned. The second layer of addresses is constant, but you are reassigning arrows. I might go over it at some other time, but now let's construct our integral. And let's see how it works. Yep, works fine. I can update it to be 12 if I want to. I can make it something weird. And this is an not evaluated, and it notes like, hey, I'm going to integrate with respect to X. Okay, so I have that. Let's exponentiate it. Why not? Okay, and now there's a simple comment. This is just do it method. So I could pass some assumptions like, hey, I'm operating on real values, assume this, assume that, but I'm not going to do it. I'm just going to tell it, hey, execute that. So here we go. Let's update it. Let's update my bounds to something that's going to be easy to check. Hop. Yep, it worked. Worked nicely. So now I'm going to import the module that searches for trigonometric antiderivatives. As I mentioned in the previous section, if you give it a hint where to search, it's going to be faster and more efficient. So now I'm going, yep, it's imported, and I am going to tell it, hey, do a trigonometric integral on my sine function. And bingo, it's minus cosine. So I have that. I could later evaluate it if I wanted to. Not sure if do it. It's going to, I would have to provide a value to it. So I'm going to look into that later. But if I want to, oh, okay, yeah, I'm doing it in the next line. So if I want to evaluate my integral at certain values, I'm applying a method, which is evaluate function. and it takes the argument of substitution. So how to read it? I define my values if I had more to substitute. So let's do it like A, well, let's make it a C. A and C is not defined, but I will make C sim. I defined Y. Let's use Y. Yep. And how does it look like? Can I see it? Probably not. Nope. Okay. I'll deal with that later. Well, errors happen sometimes, so not today. So I have that. I want to evaluate it at a specific value, so I define my substitutions. I assign to a variable, it's a dictionary, so it tells it for x, substitute pi over 4. And now I plug in into my substitutions. So I provide this dictionary to my substitution. And voila! Numerically evaluated. Remember, once it gets numerical, there's an error here. It's not exact. So yeah, something I showed during the lecture, but I like this example. When you're doing symbols, you're fine. It just evaluates this expression. Is symbol x equal to symbol x? Well, it obviously is. Now doing the pattern matching. Is it equal to x plus 1? No, obviously not, even though this is just a number. Let's do this. Still false. Still doesn't match the pattern. It doesn't match the pattern because it just checks this, and there's something additional which is non-zero. Let's see if it... Yeah, it sees this thing is non-zero, thus whatever this value is, even if it cannot store this value, it sees those are not equal. But behold, now I'm substituting 1 for x, and 1 goes on this side, and now I add my first let's add something bigger. Is it equal? This, it's not evaluating this expression. Nope. It's false, they are not equal. And now let's do the trick with zeros. Tell me, is it equal? Oh yeah, because now it got numerical. Those are just values. This is cut off. It doesn't exist. So it's 0, this is 1, this is 1, all is good. Well, no. So that's something to remember. And always when you're doing calculations, when you're doing anything, something to keep in mind is this is the computer. It gives you back what you provided, but sometimes, we didn't say it makes an error, but there might be an error in your reasoning or how you think it's going to execute it. So there's always something like sanity check, like should my solution be increasing? Should it be rapidly going to 0? There's always some reasoning to check, and also you can always run a quick program just to like have the solution ready and just test your program on a problem that you know the solution to see if it actually gives you the correct value. Like, don't trust this thing 100% because it's predictable, but what you're putting into it might not be what you think you're giving it. So it does what it's supposed to do, but you might have the wrong idea of what it's going to do with that. So now doing numerical integration. So lambda. So the structure is, from my module integrate, I use a quad function, the numerical quadrature. And the structure of it is, it takes a function as a first argument. It won't, if I just put x here, it's not going to see it as a function. I need something that is going to provide this statement. And what lambda does is, I'm telling it, hey lambda, take whatever I give you as x, a, and b, and from it, return this expression. So it actually gives us the return statement. It evaluates. When I execute that, this evaluates first. Then it substitutes the bounds 0 and 8, and I need to tell it, hey, A and B are not variables. They are just arguments. Do not integrate with respect to them. And I need to provide them, of course. So here it goes. Numerical integration. Bam. The value of the integral and the error. Let's change the bounds. Let's change my expression. Let's just make it. Because I'm not using those arguments right now, but still lambda was expecting them, so I can delete those. I delete those and evaluate the integral of just, well, let's make it simple. Nice. Okay. And now, if I want to construct a function that's going to take those arguments, the basic syntax, I made a function, it has a return statement, that's what integrate is going to care about. Function created, run it with quad, tell it what the just the variables are that I'm going, what the arguments are that I'm going to provide. Yeah, it happened during the class too, because here I go. Yeah, so that's a quick overview that will be posted on Slack and on LMS. As a reference, I might expand it a little bit and then I will let you know if it was updated. But yeah, thanks for watching my first ever screencast. I hope I didn't do terribly. Bye bye.